In this presentation, we're going to talk about the final two reaction steps that are taken in the synthesis of remdesivir.
In response to the massive Ebola outbreak, chemists discovered a new molecule called remdesivir. Our group's focus was on the latter half of the synthesis, where they isolated the wanted molecule 4B. The reaction we focused on proceeds through two steps. The first step is a bimolecular SN2 ester substitution, and the second step is a keto hydrolysis. This drug was used in clinical trials for Ebola and is now being used in clinical trials for COVID-19.
So the reactions that we covered involved two of the final steps in creating the molecule remdesivir. Our first reaction, labeled as reaction E in the paper, involves a substitution of the phosphate ester that was prepared in reactions G and H. This substitution occurs between the nucleoside-like starting material and a para-nitrophenoxide leaving group on the phosphate ester. Our second reaction, labeled as reaction F in the paper, shows the removal of the ketal functional group through an acidic hydrolysis. This step removes the protecting group and reveals the final structure of remdesivir. Note in both reaction schemes, bonds that are broken are in red and bonds that are formed are in blue.
In this slide, I'm going to talk about the roles of reaction E and F in the overall synthesis strategy. And for reaction E, the product is the 21 structure connected with 22B structure. So the starting materials will be compound 21 and compound 22B in the presence of magnesium chloride and the diisopropyl ethylamine. It results in breaking the oxygen and the hydrogen bond of the 21 structure and breaking the oxygen and the phosphorus bond of 22B structure. We also observe the substitution of phosphate ester in this reaction, which result in nitrophenolate group leave and change in the configuration of the phosphorus stereo center. So it's like SN2 reaction. And this configuration will remain the same in the final product even after reaction F. And based on the paper, the step cannot be replaced in second generation synthesis scheme. And for reaction F, the two oxygen and carbon bonds from the product E will break and it will be replaced with two alcohol groups that will remain the same in the final product structure. As we know, the oxygen and carbon bond, it's less polar than oxygen and hydrogen bond. In other words, we can say that other groups, it's less polar than alcohol group, or other group is less reactive than alcohol group. So I can conclude here that the final product with two alcohol groups is more reactive than the starting material with two ether groups. And Michael will talk more about the mechanism of reaction E and F in the next two slides.
Here's the mechanism for the phosphate ester substitution. The reaction starts by deprotonation of the nucleoside's hydroxyl group by using NN-diisopropyl ethylamine, also known as Hunig's base. The resulting oxide will become the nucleophile. We propose that magnesium chloride is used to coordinate with an oxygen atom on the phosphate ester, enhancing the electrophilicity of phosphorus. In addition, acetonitrile, the solvent, will stabilize the charge on the conjugate acid of Hunig's base, further allowing for the nucleophile-electrophile interaction. The substitution reaction that occurs is bimolecular with a concerted mechanism, giving way to the new phosphate ester. Further separation techniques are used to work up the reaction to prepare for reaction F. On this slide, we have the mechanism for the deprotection of remdesivir. This is a typical ketal hydrolysis reaction that occurs with aqueous acid. It is good to note that the starting material is mixed with tetrahydrofuran, or THF, initially. This is done to fully solubilize the rather large organic molecule before hydrolysis occurs. After this reaction is complete, the mixture is worked up with base, and separation techniques are used to finally isolate remdesivir.
On this slide, I'm going to talk about reactants of both reaction E and F, starting with acetonitrile in reaction E. It's act as a solvent. They first put 16 milliliters of acetonitrile into the mixture of 22B and 21. Then they added 360 milligrams of magnesium chloride at room temperature, and it acts as a Lewis acid. After heating the mixture to 50 degrees Celsius for 10 minutes, they added 1.45 milliliters of diisopropyl ethylamine, and a bulky base. It acts as a weak nucleophile. And moving on to reaction F, we first have THF act as a solvent. They stir the product solution from reaction E in 100 milliliters of THF, and then they add 20 milliliters of 37% hydrochloric acid, and it's act as a electrophile. One thing I want to point out here is the number for two solvent, the mole equivalent for two solvent the number look really big, but it's totally fine because it's a solvent. It have a lot of excess. That's why we have such a huge number, and that is also a reason why we have to do workup after a reaction. And I'm gonna talk more about reaction workup in the next slide. On this slide, I'm gonna talk about reaction workup. First start off with reaction E. They diluted the reaction mixture with 100 milliliters of ethyl acetate. Then the organic layer was washed with 40 milliliters of 5% aqueous citric acid solution. They keep washing it with another 40 milliliters of saturated aqueous ammonium chloride solution. And then they washed it 2 times and 40 milliliters each time with 5% aqueous potassium carbonate solution. And lastly, they wash it with 40 milliliters of brine. And the organic layer was dry over the anhydrous sodium sulfate and concentrated under reduced pressure. The crude residue was subjected to silica gel chromatography, eluting with ethyl acetate in hexane to get the product for reaction E. For reaction F, they dilute the reaction mixture with 100 milliliters of water, and then they added 200 milliliters of saturated aqueous sodium bicarbonate solution to get pH equal 8. The resulting mixture was extracted with ethyl acetate, and the organic extract was then washed with brine around 15 milliliters and dry over anhydrous sodium sulfate and concentrated under reduced pressure. So the same as reaction E, the crude residue was subjected to silica gel chromatography, eluting ethyl acetate in hexane to get the final product.
The genetic information that viruses use to reproduce in our cells is contained in RNA. Remdesivir is a molecule with structure similar to that of an RNA segment called a nucleotide. RNA nucleotides contain a phosphate, a ribose sugar, and a nitrogenous base. Remdesivir contains similar functional groups, with a nitrogenous base that resembles adenine in RNA. Acting as an analog, remdesivir is incorporated into virus DNA. Then, RNA-dependent RNA polymerase, which normally replicates the virus RNA, is blocked because remdesivir, with its extra benzene ring and ester group, does not fit properly into the enzyme. This inhibits the spread of the virus, and thus remdesivir serves as a cure. Here you can see the similar structures between remdesivir and an RNA nucleotide. You can see that both have a nitrogenous base, a phosphate group, and a ribose sugar.
New discoveries have shown that remdesivir has proved helpful in the COVID-19 pandemic. The drug is designed to interfere with the process that the virus uses to make copies of itself. The resulting copies of the virus lack their full RNA genome, so they cannot go on to replicate themselves or infect other cells. First used in Ebola treatment, Remdesivir was thought to help with reducing symptoms. Now with the new pandemic, Remdesivir is in 2 phase 3 clinical trials. One study is evaluating Remdesivir in patients with confirmed disease who have developed more severe clinical manifestations, such as a requirement for supplemental oxygen via ventilation. The other study is evaluating Remdesivir in patients with confirmed COVID-19 infection who have been hospitalized but are not displaying significant clinical manifestations of disease, such as an oxygen requirement. More studies are to come, but the results are thought to be positive.
The goal of these mechanisms was to synthesize the product 4B, or Remdesivir. After phosphate ester substitution was completed, there was a 70% yield for an SP isomer. After, mechanism F proceeded to help synthesize the final product. Once the ketal protecting group hydrolysis reaction was completed, the product 4B, Remdesivir, was synthesized with a yield of 69%. This research could also be used to help find cures for other viruses, such as the new worldwide COVID-19 pandemic.